Recently, I've had a lot of students feeling confusion about which acceleration to use in a situation or how to break up a problem. So I wanted to stress, when do formulas start and stop? When do they start working? Now, one way to understand what's going on in physics is that it's a story. Everything is an ongoing story with lots of adventures. You have a problem with a person being shot out of a cannon and flying through the air and landing on a trampoline. I ask students, what's the acceleration here? And a lot of them say, well, it's big and positive, because they're thinking about the launch, the process of going up through the tube. But of course, what the problem's primarily about is the flying through the air part, during which the acceleration is negative 9.8. So, like the example I've used before, if you have this object, toss it in the air, catch it. That's 5 accelerations. Before I started throwing, it was 0. While I'm throwing it, it's a big positive. As soon as it leaves my hand, it's negative 9.8 the whole time. And then it becomes positive big during the catch, and then it's 0 again. So which acceleration are we talking about? We're talking about the negative 9.8 part. And that part begins just after it leaves my hand and ends just before it hits my hand. So don't confuse what's happening in the air with what's happening during the catch or during the throw. So in this problem, yes, the person had no acceleration, then a big positive diagonal one. Then it was negative 9.8 for the flight. That's the part we're actually working on. And then there would be a big positive acceleration here, and then 0. A similar situation. Say you have a stuntman driving a car off a cliff for a movie. And I ask, what's the acceleration during the fall? During the fall, the acceleration is negative 9.8, 9.8 downward. But when I ask students what the acceleration is, they're usually saying, oh yeah, there's a positive x acceleration. I'm certain that the driver had to accelerate to build up to the launch speed. But that's an earlier part of the story. That's not the part we're talking about. The part we're talking about is here. Likewise, sometimes people get confused about the direction of the velocity. They're like, well, it's going downward, right? It's like, well, no, it's going to, but right at that moment of launch, you'd say the moment of launch, it's horizontal. So just for that instant, the v0y is 0. Yes, it's about to change, but it hasn't yet. Its velocity y was 0 all during this along here, and it's about to change, but it's still 0 for our purposes. We're starting the clock just at the instant after it leaves, and we're stopping the clock right just before it hits. Here's a different situation. Coefficient of friction. I have a mass here, and suppose I want to know the minimum coefficient of static friction to keep this thing from sliding down the hill. People are setting up F equals ma, and then they're asking, what's the acceleration? And I'm saying, well, it's 0, because we want this thing to hold still. And then they're like, well, isn't it not the minimum then? What, isn't it more than the minimum? And it's like, well, we're right on the edge. When you're right on the edge, you can imagine it being right on the verge of slipping, and if anybody sneezes or breathes or whatever, it will slide. So a lot of people worry about, but what if it is exactly the right amount of mu? Will it move or will it slide? And the answer is, in the real world, things are rough. So if you put it at what you try to do is exactly the value, there's going to be some tolerance on it anyway. And sometimes you put it down, it'll slide, and sometimes you put it down, it won't. And in general, you're going to have to like put it down very gently, like a safe cracker or something, in order to keep it from sliding if it's like right on the very verge of sliding. Any kind of vibration or whatever could set it off. Finally, here's one more situation. Suppose you put an ice cube or something very slippery on top of a big round ball, like a beach ball. And it starts to slide down. At some point, it's going to fall off. And then it's going, instead of being a circle, it's going to be a parabola as it goes airborne. When is it going to do that? When does it lose contact? So, lose contact, you might be saying, well, is that even physics? What are we talking about here? When did we talk about contact in physics? Contact forces. You can't have a contact force if you're not in contact. The contact forces are things that require you touch, friction, and normal force, primarily. Technically, ropes as well, but definitely not gravity, because gravity works without anything connecting the things. There's nothing tying the moon to the Earth, but it goes around the Earth. Losing contact means the contact force goes to zero. If I'm assuming this thing's frictionless, that can't be what I'm talking about. There are no ropes in view, so it's got to be normal force. We've got the normal force here, and we've got mg here, and the normal force has to drop down to zero. Because remember, normal force is your apparent weight. It's a measure of how hard you're being pressed against whatever surface. And when the normal force drops to zero, that's when you feel like you're floating, and then you can go airborne after that. All right, so I hope that clarifies a little bit that there's different parts of the story. Any situation that you're analyzing, you're just analyzing one piece of. You're taking one small chapter of the story that you know how to analyze, that's simple enough to analyze, and you have to cut the edges carefully to only include the stuff you know how to deal with. So I hope that helps you in understanding where some confusions are interpreting problems. Thanks for watching.